Hello, AP Physics students. I'm using this video to respond to some questions about the Chapter 6 work, energy, and power assignments. One question I've had asked a couple of times is a solution of problem 34. So this is an interesting problem involving conservation of mechanical energy, thinking about all three forms of mechanical energy: gravitational potential, kinetic, and spring potential energy. So we have a 62 kilogram trampoline artist jumping upward from the top of a platform with a vertical speed of 4.5 meters per second. How fast is he going as he lands on the trampoline 2 meters below? If the trampoline behaves like a spring of spring constant 5.8 times 10 to the fourth newtons per meter, how far down then does he depress it? So we're thinking about the types of energy held in this person as he moves around in this Earth trampoline system. I don't know how to spell trampoline. I-N-E. Okay, so this distance here is 2 meters. And he starts here with an upward speed, so I'm going to label this V naught, of 4.5 meters per second. So he starts out with kinetic energy. And if we call this position at the trampoline y equals 0, he also has gravitational potential energy. We could also say that the position where he begins is y equals 0. If that were the case, we would then need to label the position at the landing point, the trampoline, as y equals -2. As long as we're consistent with our sign conventions and we are consistent measuring above and below our chosen y equals 0 position, we can choose any y equals 0 position. It's arbitrary because in the end, what matters is not the individual energies, but the changes in energy. So our big idea is conservation of mechanical energy. We're not given any information about air resistance or frictional losses. So we're going to assume that there's no friction, no non-conservative forces. If that's the case, mechanical energy is conserved. And what that means is change in potential, gravitational potential, plus change in spring potential, plus change in kinetic energy, all equals out to 0. There's no net change in any of the mechanical energy. So, or in the sum of the mechanical energies. So now I start thinking about what type of energy is happening where. So I have some kinetic here, some K, and some UG, if I define y equals 0 at the trampoline. He goes up to the peak, pauses, and then falls back to the trampoline. If I'm finding his kinetic energy, or how fast is he going to land on the trampoline, then it makes sense to say y equals 0 here, because as he encounters the trampoline, as his feet just barely touch it, he has not yet compressed the trampoline. He has all kinetic, no gravitational potential, because y equals 0 by our definition, and no spring potential, since he has not yet compressed. So by setting y equals 0 here, I make my first answer a little bit easier because I don't have to worry about gravitational potential energy here, and he hasn't compressed the trampoline, so I don't have to worry about spring potential energy here. So I'm going to say that the gravitational potential energy at the trampoline, I'm calling that final, minus gravitational potential energy at the start. There's no change in spring potential energy, so kinetic energy at the end minus kinetic energy at the start. Right, there's my delta K, there's my delta U equals 0. So U final, 0. U initial is mg times 2 meters. Gosh, I guess I should just use their numbers. The mass of this person, 62 kilograms, G 9.8. And starting position is 2 meters above the ending position. So there's my 0 minus starting gravitational potential energy, plus ending kinetic energy, half mass times v, I'll call it final squared, even though it's not exactly the final velocity, but it's the velocity at the trampoline, minus half mass, mass, times starting speed, 4.5 meters per second. And that gets squared equals 0. So it's interesting to note that although he's jumping up into the air, our equation in our math is exactly the same as if he had sort of flung himself down into the trampoline, thrown himself down into the trampoline. Now, the reason I switched from 62 to mass here is that it turns out we can factor mass out, right? There's mass, blah, 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 plus mass, blah, 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 plus mass, blah, blah, blah. So I factor mass out, not the m of the meters, right? I can factor it out here and divide both sides by mass. 0 divided by mass is 0. And so I can simplify a little bit. So I've got negative 9.8 meters per second squared times 2 meters high, plus half times ending speed squared, which is what I want to find, ending speed, minus half times 4.5 meters per second squared equals 0. And now I solve for that final velocity. So I might as well actually plug the numbers in here. 9.8 times 2, 19.6. And this is meters per second squared times meters. Oh, times kilograms, right? It's like a weird, I'll just leave it as that. Plus half the final squared minus 10.125. Oh, did I actually? Yeah, I did multiply by half. 10.125 meters squared per second squared equals 0. Combine these two terms. Oh, I don't want to subtract though because I'm not keeping track of my negative sign. I made everything positive. So 10.125 and 19.6. I've got negative 29.725 meters squared per second squared plus half the final squared equals 0. We add 29.725 to both sides. And that's a good thing that it's negative because otherwise we'd be taking the square root of a negative number. I mean, it's good that it's negative here on the left side. When I bring it over to the right side, it means I get to take the square root of a positive number. So I multiply both sides by 2. And then I take the square root. And I find that the velocity is plus or minus 7.71 meters per second. I choose the minus if I'm really reporting velocity because I know that as he lands on the trampoline, he's on his way down. We could have had him jump from 2 meters below at the same speed, 7.71, going up, and at this height of 2 meters, either on the way up or on the way back down, he would still have that velocity of 4.5 meters per second. So the symmetry of the quadratic equation has physical solutions other than the one we're particularly seeking. So 7.71 meters per second is his landing speed on the trampoline. That's only part A, though. Part B says if the trampoline behaves like a spring of spring constant 5.8 times 10 to the 4th newtons per meter, how far down does he depress it? So now I'm going to redraw my page has gotten a bit messy. I'm going to redraw my diagram here. And note what I know, 2 meters. This is V 4.5. We now know this is V 7.71. Okay, and that's kind of like all the things we know now. We can still keep calling this y equals 0, y equals plus 2. That's fine. Okay, so now we want to know how far does he depress the spring. So I've got all this different information about energy, of mechanical energy at points above the trampoline, where it's combination of spring potential and kinetic, combination of gravitational potential and kinetic here, all kinetic here if I have my y equals 0 here. So now I want to consider what happens as the trampoline sort of depresses. He travels further down, right? He has a delta Y here. And that is the compression of the spring, the quote unquote compression, because the trampoline's acting like a spring. So he goes to some different Y position here. This is now Y final. And that's really what we want to know. But this number we're going to expect to be negative because it's below Y equals 0. I could consider the energy at this point compared to the energy at this point, or I could consider the energy at this point compared to the energy at this point. It doesn't matter because mechanical energy is conserved. Since this is a combination of spring potential and gravitational potential, and then I would also have spring potential and gravitational potential here, that seems like too many things to calculate. So I'm going to choose this point here where it's all kinetic and no UG and no US, right? So I only have to calculate kinetic energy at the point where he contacts the spring. And then here it's all, or I should say it's no kinetic, and it's some UG and some US. So I like less calculations. I'm always kind of trying to be lazy. But again, my big idea is conservation of mechanical energy. So I have ending kinetic energy, Kf minus Ko, UGF, UGO, USF, and USO equals 0, right? So this is 0 because it stops. This is 0 because of where we set Y equals 0 to be. And this is 0 because at the beginning, his feet have just barely tapped the trampoline. He hasn't quite compressed it yet. So I kind of simplify what I can based on where I'm setting my zeros. And now I add what I know. So half times his mass. Now this times the mass won't cancel out. I have a half mass times speed squared here. I have a mass times g times height here. But I have a half kx squared here, so there's not a mass in every term. So I can't be quite as lazy as before. 62 kilograms is his mass, and his sort of landing on the trampoline speed is 7.71. And I may need to drop the units just to fit these terms on the page. Okay, so that's 0 minus kinetic energy at the beginning, plus gravitational potential energy at the end. So that's 62 kilograms times g times y, and I'm just going to leave it as y, but I'm going to expect to get a negative number because I've gone below 0. Oops, and that should be a negative sign. No, that should be positive, excuse me. Minus, plus, minus 0, plus, positive. So then plus half times the spring constant, 5.8 times 10 to the 4th newtons per meter times y squared equals 0. These two y's are the same. This is how far down he drops from the edge of the trampoline to its compression point. This is how far down he drops from the edge of the trampoline to its compression point. So I'm solving, unfortunately, a quadratic equation for y. So the form of this quadratic equation, then like all my little A, B's, and C's. Let's see, I'll find A first. I'm going to rearrange it so it's A y squared plus B y plus C minus C. All right, so I guess that should have been an easy thing to do. I can leave this at, I'm just going to leave it as a whole number, 29,000. And I'm going to drop the units because otherwise we're totally running out of room, right? This is a unit of Newton per meter or kilogram per second squared. Yeah, because it'll end up being kilogram meter per second squared times meter. Anyway, the units will, oh, it's meter squared there. Yeah, what a mess of the units. We're just going to say 29,000 y squared plus 607.6 y minus minus 1842.77, right, equals 0. So here's my A, here's my B, here's my C, noting that C is a negative number. And so we'll say y equals negative b plus or minus the square root of b squared minus 4ac over 2a. And I'm totally not solving that quadratic equation. We are going to assume that the solutions are correct this time, finding that the y position is 0.26 meters. And that should be your answer. Please email me with any questions about this problem or any further questions about this problem. Bye.